Good morning, everyone. My name is Francesco Maiorano, and I serve as AI and machine learning scientist with the Digital Transformation Office here in Naples. I joined Hitachi 3 months ago after working for a few years in research institutes and companies on machine learning for computer vision, natural language processing, and anomaly detection. I hope to be the first new hire of many machine learning scientists here with the Digital Transformation Office. And I'm really glad to be here, and I thank the organizers for the time to tell you a little bit about the ongoing activities and processes we have here at the DTO. So let's start with what is our reference in our work, which focuses on multiple aspects of our company. The core, the platform, and the people. So starting from the core, we identify three main areas for which we want to improve digital maturity and enable machine learning. So our product, where we imagine the train of the future, which is a sensorized and proactive machine, which enables predictive maintenance, autonomous or assisted driving, and also focuses on customers and provides customer entertainment. Our operations and our factory, where we aim at switching to a digital factory through advanced robotics, connectivity, and to streamline support functions such as supply chain processes and warehouse management. Also, we include here part finding or automatic suggestion when a failure is detected. And on the other hand, field activities where by deploying a health check monitoring suite for prognostics. At the foundation of this vision lies a proper digital data platform based on IoT systems and devices and data ingestion through data lakes and analytics for analysis. But even more important are the people, as for us machine learning provides algorithms that seem intelligent. So we want to leverage a network of people's intelligence together with machine learning algorithms to achieve more. And finally, digital KPIs allow us to monitor our progress and change pace when needed. We can see here a summary of some of the main topics to which we are sensitive, from advanced driving or assisted driving to telecommunication system for diagnostics. We leverage live data streams from the train to our control room to allow deployment of machine learning algorithms. We also focus on security in terms of cyber security and also video analytics for security inside the train. And also, as we believe rail is the mobility of the future, we aim at being environmental friendly. From a factory perspective, we can deploy a similar approach, a similar methodology and vision. We aim at providing design and production. We want to better integrate design and production phases. And we also want to, by turning the factory digital, this would allow us to better monitor production progress even in real time. So the information that is gathered from production robots can be used to perform predictive maintenance, keep downtimes, and suggest parts to buy when it's needed, and so on. Here we summarize our vision over three perspectives. The operator with a prescriptive algorithm suite, health check monitoring, and consumption optimization. From the manufacturer perspective, with advanced analytics for testing, for instance, and operator perspective with maintenance optimization tools and spare parts management, and supply chain analytics. In particular, our framework is divided in 5 layers, starting from data collection by leveraging IoT devices and sensors to collect time series on main components, data integration for pre-processing, aggregation and summarization, data management on cloud-based distributed data storage systems such as data lakes, and analytics for description, prediction, and prescription as 3 steps, and data visualization to guide the entire process. So there are 3 major steps that allow us to extract knowledge from data, gather, transform, and discover. And the idea here is to characterize behavioral patterns of interest on the basis of data that is monitored from the process or assets under study. We could refer to this data as training data. This is done by means of mathematical algorithms, such as machine learning models and statistical analysis. And the acquired knowledge can then be applied to new unseen data, test data, to tackle a wide variety of problems such as classification, regression, or clustering. So in order to enable our, what we call D-Cube approach, and enable health check monitoring, exploratory analysis, and machine learning, we apply the CRISP methodology, cross-industrial standard process for data mining, which builds upon a standard process cycle for data mining towards conceiving it as a series of steps along a workflow. So we start from business understanding and data understanding and exploration to the evaluation of and training of the models, going through data preparation and modeling. So once we have the models ready, we can deploy them in an online monitoring platform. And their output can be critical alarms, optimal scheduling, and so on. This is a standard machine learning process in line with CRISP, which starts from data collection and ends in production. The intermediate phases allow design and development of machine learning algorithms. And in particular, the 3rd phase, exploratory data analysis, allows to both guide feature selection, model training and evaluation, but it also gives a backward feedback to the preceding phases, such as data collection and preparation, as we might want to include design choices in the pre-processing phases. Machine learning can be used in several fashions. We report here 2 of these, supervised and unsupervised. The first relies on both input and output data, with which we can perform classification and regression. Some examples are prediction of remaining useful lifetime, classification of failure within a given time window, flagging anomalous behavior and time series analysis. With unsupervised, we only rely on input data, with which we can perform clustering and therefore try to extract a structure that we can detect in data. Some examples are feature selection engineering, in cluster analysis, finding the optimal number of clusters, fuzzy clustering to handle uncertainty, so a sample can belong to multiple clusters with a probability, and outlier detection. Anomaly detection in a fleet involves different aspects, from security to heterogeneity of the data, efficiency in large data volumes, and information fusion is needed to make sense of all the different monitoring systems. But the reality of data mining really lies in the middle of 2 extremes. On one hand, we have each system in the fleet which is treated as unique, and we can monitor that system to detect significant changes in the operation. On the other hand, we have a group of systems that is manufactured the same way and is intended to be used the same way. So we can monitor and use an aggregation of data over different instances of the fleet to model a common behavior, and then use that knowledge to detect new unseen behavior that may be anomalous. that moves away from the common behavior that we detected. That is all. Thank you very much.